Good day, DeWolf Chemistry students. It's me, Mr. Cheney, with another brilliant tutorial. This one, less brilliant than others. It's really just note-taking, but this is the notes that we did on Monday for our first chemistry chapter in the book for the second quarter. So let's get started. It's about states of matter. Once again, as a reminder, when we do vocabulary annotations, we are circling the words and highlighting the definitions. If you're not sure what the definition should be, you can click on the word and it will give you the definition right here. So the energy of an object's motion. So I would suggest circling words then highlighting afterwards. So let's just run through it really quickly. There are other things to be highlighted besides vocabulary words in this section of the book, so pay attention to that as well. There's some tricky spots with like diagrams and stuff. So the two words on this page, kinetic energy, kinetic theory. We've known about kinetic energy before. That's not new to us. Kinetic theory describes all matter as tiny particles that are in constant motion. Okay, moving on to the next page. We've got standard temperature and pressure, otherwise known as STP. It's a standard set of conditions used for comparing properties of different gases and corresponds to a temperature of 0 degrees Celsius and approximately atmospheric pressure at sea level 100 kPa. The elements that exist as gases under STP are indicated on periodic tables. The elements that exist as gases under STP, or standard temperature and pressure, are indicated on the periodic table. So over here on the right, gases can be elements in pure form or compounds. The elements that occur naturally as gases at STP typically populate the right side of the periodic table. So helium we kind of know from filling up balloons. Nitrogen is in the air that we breathe. Oxygen, fluorine, neon is like that gas in those signs. Some of these other ones you may have heard of, like argon and bromine. Next page. Gas pressure. Definition: the result of forces between the molecules of gas and the container walls. We want to highlight this as well. So this is in addition to the vocabulary words. This can be done by shrinking the container, adding more particles, or speeding up the particles. Same thing with this annotation here. Temperature, volume, and pressure. Changes in temperature and volume affect the speed of the particles and the number of collisions between particles. So this diagram right here very clearly shows those in action. Okay, little section right here that is easily missed if you're not looking for it. We want to know the difference between PSI and kPa. So PSI, pounds per square inch, and kPa is the scientific measurement for kind of the same thing, and it stands for pascals. So they want us to convert between those two. We're not going to. It's unnecessary math in my view, but I do want you to know the difference, like as far as definition, PSI versus kPa. We're not going to do this math during this lecture. Now, this is the most important part of this chapter as far as how particles move when we're talking about solids, liquids, and gases. So the three ways: translation, rotation, and vibration. So the definition of translation: body shifts from one point in space to another. That could be left, right, up, down, diagonal. Rotation is a body spins around a fixed point. So think of the Earth spinning around on its axis out in space, getting its 24 hours. Takes 24 hours to do one rotation. Vibration is an object moves rapidly back and forth but stays in a fixed space. And down here, make sure you get to the bottom of the page. We're going to be making these annotations as well. So for gas, particles are free to move in all three ways. So you can see that all three of those, gas is the most excitable, most moving particle. Liquid, close proximity and attraction between the particles limit translational movement. So it does kind of have translation, but not nearly the same amount or type as gas, but it does have all three: vibration, rotation, translation. A solid, particles are close together and have strong attraction to each other, resulting in only vibrational energies. So solids only have, of the three, vibration as movement of particles. Okay, fluid is a vocabulary word: any substance that flows. So both liquids and gases can be considered fluids because they both conform to the shape of the container and can flow into them. Other examples obviously are like water, and we have syrup and honey, and anything that flows is considered a fluid. Here's another part of the text that we need to highlight, even though it's not a vocabulary word. The strength of the attractive forces between particles that bring the particles closer together are what distinguish a liquid from a gas. And anytime in the textbook we see larger font with a blue flag, that's an important piece, so we're going to do that. We're going to highlight that. Identifying patterns in the strength of attractive forces helps explain the behavior of different substances and states of matter. So when we get into bonding, we're going to talk about 3 different types: ionic bonding, covalent, and some other bondings. That's going to make a lot more sense. So this is just a diagram of how fluids will flow. Okay, here's kind of a tricky part because we've got 2 words that we have to define. The first one, intermolecular. The second one, intramolecular. So the difference is this. Intermolecular is the attractive force between different molecules, and intramolecular is the forces that hold atoms within an individual molecule together. So this would be like H2O, the bond between the 2 hydrogens and the oxygen. Intermolecular would be like 2 different molecules like sodium and chloride bonding together to form table salt. Solids, we're going to highlight this. The particles are packed together closely such that the intermolecular forces are very strong, or all of the particles are actually bonded together. And so we're going to circle all these. These are the 4 types of solids: molecular solid, ionic solid, metallic solid, covalent solid. We want to highlight these features for these 2 right here. And those 4 that we just circled, we're going to circle again, and these are the actual definitions that you want to go through. Molecular solids consist of molecules that are held together by the relatively weak intermolecular forces. Because of these weak molecular connections, molecular solids tend to be soft and have low melting points. So if you think of an ice cube, that's H2O that's frozen. If I put it in my hand, it's going to melt. It's got a low melting point, and it's weak. So you can break apart water, especially solid water, pretty easily. I could throw an ice cube on the ground, it breaks pretty easily. Ionic solids consist of positively and negatively charged ions held together by ionic bonds. This relatively strong attraction results in high melting points and hardness. So think table salt. It takes thousands of degrees of temperature to melt salt. It's not easy to melt salt. You can heat it up on a stove, no problem. Metallic solids formed via strong metallic bonds. However, the properties of metallic solids are highly variable and depend on exactly how the electrons are arranged. And then lastly, covalent network solids consist of networks of atoms held together by covalent bonds. Covalent solids are very hard and tend to have the highest melting points, so think diamond with covalent bonds. Okay, last few words. Crystal. The definition: particles are arranged in an orderly, repeating, and 3-dimensional pattern, and that is called a crystal lattice. Not all solids are crystalline. There is something called an amorphous solid, and that's something that lacks an ordered internal structure. So if you were to look at the components of rubber, plastic, or asphalt, you would see that it doesn't really repeat or have a 3-dimensional pattern, or it's not arranged in an orderly fashion. It lacks order. And last thing that we're going to highlight is something about unit cells. So how closely atoms are packed within a crystal unit cell affects the physical, electrical, and mechanical properties of a material. So here's all the different types of structures that a crystal can be kind of arranged in. And cubic is interesting because if anybody's ever heard of cubic zirconium, that is a fake diamond, and so its structure is much, much different than a real diamond. And that's kind of why diamonds are rare and valuable, because of their structure and the properties that they have. Cubic zirconium looks good, made by man, but the structure is much different, weaker, and so forth. And that's it. That is the chapter on states of matter, at least the first part. If you got all of those down, click. You're going to see a blue turn-in button up here. Go ahead and do that. and I'll see you back in class.